This is a map of perfect play of Connect 4. Each branch emanating from this central node is a different Connect 4 opening. Some are long and convoluted, but don't have much room for deviation, like this long unbranching line. Some, on the other hand, have a whole bunch of variations on the same theme, as indicated by this large blob of opportunities. But how can we come up with a Connect 4 solution like this, which fits in a cute little graph? We start by imagining two omniscient gods playing a game of Connect 4. Players take turns dropping discs in the columns, and the first to make a line of 4 wins. What would happen? God 1, playing red, realizes that if he plays in the leftmost column, there is no path to victory. Starting one column over, he would lose as well. Starting almost in the center, he foresees that perfect play would yield a tie. But playing right in the center should result in victory, even against a flawless opponent. God 2, playing yellow, comes to the same realization and promptly resigns. After analyzing millions of variations of every opening imaginable, God 2 realized there was no way of stopping God 1 from making a red line of 4. This was first discovered independently by computer scientists James Dow Allen and Victor Alice in 1988. They used strategies similar to the gods, using computer programs to search millions of possible branches. Solutions like these make for great computer science. But as a human Connect 4 player, it kind of leaves you wanting. Player 1 wins by playing in the center, but why? A computer, or a god, can evaluate billions of positions to check this result. But what's left for us humans? After player 1 plays in the center, what player 2 openings make it as hard as possible for player 1? To confuse red, should player 2 respond in the center? Or 1 over? How about all the way on the side? Furthermore, is there some change of perspective that shows how us mortals could hang on to the player 1 advantage and defeat a perfect player 2? These questions went unanswered by those early solutions to Connect 4. But today, I'm going to show you Connect 4 through the eyes of God 1. A simpler, more elegant solution, small enough to show on this screen. Because instead of relying on brute force search, I found a profoundly simpler way to play perfect Connect 4. All it takes is this graph. Suppose you're going to play as red, and you want a strategy to play your next game of Connect 4 perfectly. What options are there, besides running brute force search in your head? Instead, you could memorize every possibility up front. That way you can just recall the right response during the game. Well, you'll need to memorize 90 gigabytes of Connect 4 data, as this poor soul found out. These two strategies, brute force search and upfront memorization, both involve a large tree of positions. The difference is that just reading ahead makes you think a lot, and memorizing branches makes you remember a lot. The amount of positions to memorize up to a certain depth grows really fast. There's one empty position, 7 options for the first move, 49 two-move continuations. After 5 moves, there's 4,000 possibilities. And by the time we reach move 10, the number of positions we need to memorize is in the millions. Plotting the amount of positions up to n moves, we get a curve like this. Classic exponential growth. Now, after n moves have already been played, if we plot the amount of work needed to brute force solve the rest of the game, the amount of reading ahead required follows an opposite curve. For a game like this that's almost over, there's much less work needed to read through it compared to brute forcing the opening position. This suggests a hybrid approach. Memorize all positions up to the mid-game, and then we switch over to reading ahead. In other words, by balancing thinking hard and memorizing a lot, we can avoid these exponential explosions. This is why chess players memorize openings. By memorizing openings, you can avoid the potential for making a mistake reading ahead, up to a certain depth. Eventually, the breadth of variations reachable at some depth is not memorizable, and you have to start thinking ahead. Victor Alice published a Connect 4 solution like that in 1988. He found a table of 500,000 perfect openings and a computer algorithm to solve endgames in a few seconds. Now, I don't know about you, but I can't memorize 500,000 positions. Before I show you how to shrink that number by a factor of 100, let me explain the trees that I've been showing in the background. If we add every possible Connect 4 position to a tree, we get this gigantic thing. This full game tree up to move 5, taken as a guide on where to play, is called a strong solution. However, it includes nodes where player 1, red, has already blundered. Remember, God 1 determined that starting all the way on the side is a losing first move. But it's recorded inside this strong solution graph. We don't want to memorize moves like those, since we'd never play them. So let's grab our hedge trimmers and snip out all the mistakes. We get this smaller tree. We can shrink it further though. Consider this position. It's red's move, and there's 2 winning options. Red could either go here, or here. Everything else would be a blunder. Those 2 nodes are in our tree. But why memorize duplicates instead of just memorizing the one we like better? Let's delete each duplicate option. This tree is sufficient. We can still play perfectly up to move 5 by memorizing it. We've just cut out all of the stupid variations that we don't need. For that reason, we call this not a strong solution, but a weak solution. Check out this game. It's red to move. Red is winning here. What do you think the weak solution looks like for this position? I'll give you a few options. Do you think it looks like this messy tree? Or this other messy tree? How about this third messy tree? Or do you think that it looks like this nice pillow shape? This isn't some trivial question about appearance. If the weak solution is particularly simple, that means we can compress the information contained within it. So make your guess. Which one do you think it is? The answer is all of them. Remember how I chose between 2 winning options earlier? Up to the choices we make, we can get much different trees. This tree is what you get if at any time there's a decision between 2 winning moves, you always choose the leftmost one. This tree involves always picking the rightmost option. This tree involves picking randomly between the winning options. But how on earth did I make this one? How do we identify these patterny weak solutions? I use what I call a steady-state diagram. The diagram is like a cheat sheet, telling red how to make all the right moves from here until the end of the game. To read it, there's a series of 8 priorities. It's red's turn. Let's follow the diagram to win the game. Rule 1. Can we win by making a line of 4? Nope. Move on to Rule 2. Is the opponent about to win, such that we need to block it? Nope. Continue. Can we play on an exclamation mark? Yes, that's the move we'll make. Now, remember, this secret diagram tells us what to do, but our opponent can fight back however they want. Our opponent chooses to block the threat. What should we do now? The first rule that applies now is Rule 6, which says to play on a plus sign. Our opponent responds here. Try and figure out what red should do next, according to the rules. There's only one @ sign available now, so red plays on it. As red, if you follow this cheat sheet, regardless of what yellow does, you'll eventually win the game. These diagrams are effectively a form of compression. By identifying such a simple program to play perfect endgames, which describes a very compressible solution for our position, we can memorize that program instead of some convoluted search tree. So, what is the cheat sheet for the starting position? Unfortunately, we're not that lucky. These diagrams are only good for describing mid-games when the path to victory is already somewhat well defined. So, we're back to building trees. But this time, we can trim positions which have a steady-state solution, leaving us with the graph that I showed you in the start of this video. This is once again a weak solution, but at every leaf node, instead of the game being over, we instead have a steady-state diagram showing how to continue perfect play after that point, implicitly defining the remaining compressed game tree. This is just the compressed subgraph resulting from one particular leaf node. Imagine having to memorize one of those subtrees for every single leaf node on the graph. That's the degree of compression we're dealing with. The first thing you might notice about this graph is that it's symmetrical. This makes sense. If yellow plays on the left versus on the right, we'll respond in a way that is mirrored horizontally. There's a few exceptions to this rule. For example, this branch only has one asymmetric copy. In this case, both players made a perfectly symmetrical opening, and red must pick a side to continue on. This opening is called the 6-1 because of the central column of 6 and neighboring column of 1. Let's shrink the graph even further by fusing together mirror symmetric nodes. This Connect 4 solution has only 4,550 nodes. Comparing against Victor Alice's solution from the 80s, Alice's opening book was more than 100 times as large, with 500,000 nodes. Furthermore, unlike the few seconds of search that Alice used, we don't need any search whatsoever since the steady-state diagrams instantly tell us what to do in the endgame. This graph serves as a map of Connect 4 openings. Long branches represent openings which don't quickly simplify for player 1. They correspond quite well to openings which Connect 4 players actually study and practice. And this is great. It provides a framework to measure the difficulty of openings. For example, if player 2 plays like this, with player 1 following the solution, we run into a steady state right away, meaning yellow didn't play a very challenging opening. What about the hardest opening for player 1? The first move which preserves the longest downstream subgraph is 1 off from center. Red, following the solution, is left with 2,727 downstream nodes. One of the largest branches can be reached like this. It's the depth 8 position with the most downstream nodes. For Connect 4 players, this probably isn't surprising. This is a very popular, very challenging opening. The center column openings come in second place, also contributing a lot of nodes to the graph. These first central moves are entirely forced. From here, a large amount of nodes are dedicated to variations of the candlesticks opening, which involves making towers like so, which is also forced. We've covered a whole bunch of solutions to Connect 4. Brute force search relies intensively on reading ahead, but needs no memory. Memorizing the whole game tree beforehand takes up a ton of data, but no CPU. We can balance these extremes by memorizing openings and searching at the end, demanding just a little memory and just a little compute. And finally, we can use pattern recognition to compress the tree up front, demanding even less memory and compute, at the behest of a lot of resources used in upfront data compression and pattern identification. In each case, we're just making trade-offs between different resources. Want to use less compute? That comes at the cost of other resources. This all begs the question, where is all this complexity coming from? A strong solution lookup table for the game takes up 90 gigabytes of data, and yet the rules of the game can be defined in a single sentence of plain English. This video isn't about Connect 4. It's not entirely about computer science either. It's about how systems yield complexity that can't be expressed in simpler terms. Just knowing the rules doesn't mean you can win without somehow relying heavily on computation, raw memorization, or something. You can't just intuitively realize that the candlestick's opening is a naturally arising strategy. Similarly, just knowing the laws of particle interactions doesn't mean you can predict the weather. And it doesn't tell you that there's such a thing as a cloud. But that doesn't stop us from discussing candlesticks' openings or clouds. Maybe we can't concisely explain them from first principles, but that doesn't make them any less real. Clouds are best described not in the language of particle interactions, but in the language of cold fronts, dew points, and vapor pressure. A whole new philosophy spawned out of thin air, far abstracted from any rules of physics or chemistry. Read all the physics textbooks you want. In none of them will you find the rule that cirrocumulus clouds cannot have species volutus. There is no such rule, and yet we live in a world of intricate species of clouds with a whole subfield of meteorology concerned with their nomenclature and taxonomy. Connect 4 shows us a glimpse of that same emergent substance. It shows us that complexity and mystery aren't unique to those laws of physics which gave us stars and galaxies, benzene rings and toothpaste, but are a mathematical inevitability more fundamental than physics, more real than reality. Equivalent magic arises from even the most humble systems of iterated rules, and this game is no exception. Complex enough to invoke that same spark of emergent fertility in full force, but simple enough that with modern computers, I can show you this graph and say, here is its shape. This is Connect 4. This has been 2Swap, with music by 6884. I claim to have made a Connect 4 solution that's human memorizable, so let's put that to the test. I made a flashcard deck using the spaced repetition memorization app Anki, which I will attempt to learn. If you want to try too, you can download the deck in the description. I've also included a website where you can play against the weak solution, and explore the tree as you traverse it. Good luck winning, you'll need it. The site includes a lot of technical details which I glazed over, so be sure to check it out. I think that the best way to learn the game is to play online, and in between rounds, review the variations you played in the tree to see what a better response could have been. And that's where our sponsor, Opera Browser, can help. Using Opera's split-screen browsing feature, you can easily replay your games in the tree alongside your online matches. In this case, we can see that I played out this variation of the 6-1 exactly as suggested by the solution graph. Want to read while waiting for an opponent? Just add another split-screen window. Opera lets you split your view into 2, 3, or even 4 windows simultaneously. I found myself using Opera's tab islands to organize positions which I was in the process of analyzing. Opera automatically groups your tabs to keep everything in place, and you can name or color code these islands so you know exactly where your research is at a glance. I guess you could, use these features for organizing your research or travel plans or something, but who am I kidding? This is practically made for Connect 4 study. Opera is top-notch for productivity, especially with its sidebar that puts Google services like Gmail and Google Calendar just one click away. I can quickly check my schedule and my email without ever having to leave the page I'm working on. It also makes the YouTube experience more enjoyable. It has a video pop-out feature so that you can drag the video outside of your browser window, letting you pretend that you're getting research done while watching 2Swap instead. To try out Opera for yourself, click the link in the description to download it for free.